Good evening, everyone. So today we,
Good evening, ma'am.
yeah, good evening. So today we have the revision session for week 9 and 10. So let's start that. I hope yesterday week 9 questions are done. Okay. So in week 9 and 10, what we are mostly looking at is Perceptron algorithm. Then we are looking at logistic regression and SVM, hard module SVM. Right. So let's start now. Let's start with the perceptron algorithm. So, like from week 9 onwards, we have started looking at mode classification algorithm, right? And in like perceptron, logistic, or to say like we whatever models we are seeing after from week 7 onwards are for classification. And mostly what we are like when we start with, let's say if we start with perceptron algorithm, if we start with perceptron algorithm, then so we are using this algorithm for a binary classification problem. And what is the goal in perceptron that we have? So the goal of this algorithm is to come up with a decision boundary that separates your data set in such a way that it like correctly classify your data set into two classes, right? So goal is to determine a decision boundary. Determine a decision boundary that separates the data set. That separates the data set into two classes, right? So this is what we are trying to do. Now, what is like how does the data set look like? So my data set is this x1, y1, so on to xn, yn, right? And here each of these xi's were in RT and my yi belong to plus minus 1, right? We have two classes, class minus 1, class 1. So for the perceptron algorithm, what are the assumptions that we make? So what are the assumptions? So the assumptions that we make is the very first assumption is that probability of like given x, probability that y takes the value 1 should be 1 if, so this is equal to 1 if my w transpose x is greater than equal to 0 and 0 otherwise, right? So this is a very simplest assumption that we make for our perceptron algorithm. And what is the second assumption that we make? Uh, Another assumption that we make is this is linearly separable. So linear separability, right? Right. So when we say linear separability assumption, what do we mean? It means that if we can find, let's say, hyperplane that correctly separates, like that decision boundary or the hyperplane correctly separates my data set into two different classes. So my data set should be linearly separable. That is another assumption. So next is that in classification problem, like what is it, like what is the problem that we are trying to solve? So the problem that we were trying to solve is to we wanted to minimize the loss function, right? We wanted to minimize this loss function, which is defined as indicator of indicator of uh, if h is the model that we learn, so h of xi not equal to yi summation, okay? And h here belongs to strip x, strip h. So we had seen that this is a problem that is very difficult to solve, and we call this an NP-hard problem, right? So using perceptron algorithm, how do we find a solution for uh, for this question, right? How do we find a solution that gives you an H, which is, or that gives you a W, which is like which separates the data set in clearly into two classes. So what does the algorithm says? So what is the algorithm for perceptron algorithm? So the very first thing is that we first initialize my W naught, right? Here 0 is in RD. Right? Then the next is that until convergence. So just two steps in the algorithm. So very first thing is you initialize W naught to be 0, and until convergence, you are going to check. You are going to check. You'll follow this. So what will you do here? You will select any xi yi from the data set. You select xi yi from the data set. Now, if your sign of W transpose xi, if this is equal to yi, then we won't do anything. So saying that sign of W transpose xi is exactly equal to yi, it means that it is correctly classifying whatever W we have, it is correctly classifying my data point. So in that case, we will do nothing, right? Else, what do we do? Else, we will do the update, and that update is WT plus 1. So this is small t. Oh, sorry. This was for transpose. No? Okay. So WT plus 1, you will update this as WT plus XIYI. Okay. And end. So it's just two-step process in Perceptron. So the very first thing, like if you're, say, given a data set, you initialize a W by 0, and 0 is an RD. So until it converges, meaning that if you reaches to a point where your algorithm is no longer making any mistake, or every data point is on the correct side with respect to that W, then we can say that we have reached the convergence. So until convergence, we are going to follow this step. Okay. And the step says that you pick any data point from the data set and check this. Check for sign of WT transpose XI by XI, right? And if this is equal to YI, then I am not going to do anything. So it is already on the correct side. If it is not equal to YI, then what do we do? Then in that case, we update it using this rule. So now WT plus 1 is WT plus XIYI. So now whatever W you get, now this is your new W, and then you will check for your data point with respect to this new W that you get. Okay, and this keeps on repeating. And once you reach convergence, you will stop the process. All right. So this is Um, okay. Is there anything?
Ma'am, I have a doubt. Hello?
Yeah, yeah, you can tell.
Yeah, ma'am. Yeah, here if my W transpose X is 0, so it will go to which class? Positive or negative?
Okay. So you're saying W transpose,
X
hmm,
is 0.
W transpose X is equal to 0. So remember, like when we started, we saw that if W transpose X should be equal to 0, I am going to assign it as 1, right? So it goes to class 1.
Ma'am, if we put as a negative, so it will my W will converge.
What if we put what as negative?
If my W transpose is 0 and if I put this 0 in negative class,
Okay, then it will classify it as -1.
no, no, at the end my W will converge. If I put
See,
it in a
this
negative class,
no, this has nothing to do with convergence of W, like depending on how do you define this, right?
no, ma'am, I know that, but I'm asking if I put in a negative class,
Hmm.
so it will at the end the W will converge.
Yeah, yeah, it will. Perceptron algorithm always converges. It will.
Okay.
So remember that we have defined it in this way, and that's why, like when W transpose X is coming out to be 0, we are putting it in class 1.
But ma'am, we saw a question where the classes were oscillating and it was not converging. The this
Correct.
algorithm.
Correct. So yeah, so that is another assumption that we are going to go into, right? So we assume that it shouldn't be just linearly separable. There should be some margin to it.
Ma'am, I have one question. I have a doubt. One question exactly in this topic. Can you solve this, ma'am? Exactly this topic, ma'am.
Okay.
There is taken one and -1.
Um, what is the question?
Yeah, question is I'm telling this same topic.
Okay, you can paste it in the chat box. Let's complete the theory and then I'll come back to the question that you have. Okay.
Yeah, sure, ma'am. Yeah.
Okay. So yeah, so this is the algorithm for perceptron. So when we see this update rule that this perceptron has, it makes sure that whatever W we choose in the next iteration, it's actually moving in the correct direction, right? So we had also seen this part. So what is the update rule?
One,
Or yes,
one question, ma'am. One question I have.
mm-hmm.
Hello.
Tell me.
How can we find that the update rule we are applying in Perceptron, the W is in the right direction? From
Huh,
what value we will decide?
yeah, see. So the update rule is WT plus 1 is equal
Yeah,
to
that is
W
okay. Yeah.
plus XI
Yeah.
right? So we had seen that there are two type of mistake that can happen. So what is the first mistake that can happen? Uh,
First mistake, if WT transpose Xi
that
is
you
greater than equal to 0 and the actual is -1.
-1, right? So
And the
that
second
is
is
predicted it to be
transpose Xi less than
predicted
0
to be
and
1,
yeah, 1. Okay, that is okay. That I know.
that you know, right? But
But
actually it's -1.
how we will find it? If this update, how we will find from the value of W that it is in the right direction? Suppose we are doing.
No, we cannot. Okay, so see, you are saying if you are solving a question and
Yeah, yeah, yeah.
you have a W and you are saying that okay, how do I see that we are going in the right way?
In the first step, you got WT plus 1. In the second step, I got WT plus 2. Then
Right. Yes.
how
So
we will find? Yeah,
see, that is the numerical part of it. But if you look at this, I mean, if you look at this update rule,
yeah.
we are talking in general, right? This is in general. This is not
That I know, because what the rule has been defined, but
yeah.
how?
So if theoretically we are able to see that the kind of mistakes that are happening over here, my W, whatever W we are getting in the next iteration, WT plus 1, in both the cases, we saw that when it was actually, when actual was -1 and predicted was 1, this WT plus 1 was becoming lesser, right? It was
That
becoming,
is my question. Whether in all the cases WT plus 1 will be lesser than the WT? Is it? This is my question. Because generally we understand by the two conditions, no? But in the case of numerical problems, whether it will happen in all the cases, the W is reducing in all the steps. Is it?
W is, when you say W is reducing, I mean, you are saying W, you're just seeing the dimension of W, is it? Is this 31? No, no, no. So see, this is not.
It is not like that. It is not.
No. So WT plus 1, I mean, if you take the dot product of this with the xi,
Yeah.
right?
Yeah.
So then we are seeing that, I mean, the value is reducing. So whatever the value was earlier, now it will reduce.
Okay. This value will reduce always. WT plus 1.
Yes.
WT plus 1 transpose xi will always be less than the WT transpose xi. Is it?
Theoretically, yes.
Okay.
But see, we cannot check for every like every example and see. Maybe
Okay, fine. But that's why I'm asking, because there is a line in the lecture also. Update rule pushes W in the right direction for xi.
pushes in the right direction.
Yeah, but what is the right direction?
Yeah, so that is what, like, at every update that you are doing here, like whenever there is a mistake, like we have seen this, right?
Yeah, yeah.
So whenever there is a mistake, like let's say this was my original W. Then we did some with using some update rule, we got another W. Maybe this is my new W now.
Okay, what you mean to say that not the value, not the absolute value of W, but the direction of the W will be okay.
Yeah. So it's not about the dimension. I mean, it's not about the length of W. It's about the W which you have. Like at every iteration, the W which you have, it is moving towards the right direction eventually.
Got one. Direction is
the point you will reach to, the perceptron algorithm says that you will be able to find a W that correctly separates my data set into two pieces.
That I got. The direction, that this is concerned with the direction only, not the value. Okay, fine.
Yes.
Thank you.
Okay.
Just one question, madam. One question. You know, like you just told in the beginning, W transpose X greater than or equal to 0 is basically plus 1, isn't it?
Class 1, yes.
Yeah, plus 1. But that, if I apply, I'll give you a small data set. 1 is plus 1. You just can write down. 1 is plus 1.
Oh, hold on.
1 is plus 1.
1 is plus 1.
Plus 1. Then 1 minus 1 is minus 1. 1 minus 1 is minus 1. Yeah, okay. Minus 1. And last one is minus 1. 0 is minus 1. 0 is minus 1. Yeah. So what will be the final, convergence W?
It will swing.
Okay. Let's see. So you have 1, 1. So 1, 1 is, say, here. This is my 1, 1. This is class 1. And then you have 1 minus 1. So 1
minus 1. That is minus 1. Yes.
Class 0 and minus 1, 0.
Minus 1, 0. Yeah.
Right. So this is minus 1. This is negative class. So we want to know what is the final W that we get, right?
Yeah, right.
Okay. So let's start. So the very first thing, what we will do? My W now.
Yes.
0, 0.
0, 0, 1, 1 is 0.
So now if we take, now what we will do? We will check.
The first one will not change.
First one will not change, but the second two. So W not transpose let's call it
Will
x1.
change.
Let's call it x2. Let's call it x3. So W
Correct.
naught transpose x1 sign is okay.
It's okay.
W naught transpose x2 sign will
It
change.
will change. And we'll update that with, -1 plus 1.
Change. So this
So
is this will
-1.
change. This will change, right?
This will change to, the sign will change to -1 plus 1.
So now let's
0,
pick
0, yeah.
let's pick my x2. Okay.
Yeah.
So what is my x2? 1 minus 1.
So this will change.
1 minus 1. Right. So this need to be updated. So what is WT plus 1 now?
Is
So
1 -1 plus 1.
Like W1. So W1 is equal to W naught plus
Zero,
x2
W
y2.
naught. Yes.
Right. So W
That
naught
will be
0 0
0, 0. And that is -1 plus 1.
1 minus 1 and y2 is minus 1.
-1. So -1 plus 1.
So this is minus 1 and plus 1.
Plus 1. Right.
Right. Now this is the W I have. So check again sign of W1 transpose x1, sign of W1 transpose x2, and sign of W1 transpose x3. Okay.
So every time you start once again from the beginning, or you should go from W2 x2 to a W3 x3? That's my question.
From the beginning.
So every time, whenever you're taking an update, you will go from the beginning.
Yeah, you check it, because see what if the W that you get right after one step, it correctly classified, then you don't have to do it, right?
Okay. So you have to once again go back to W1 x1.
So it will be 1 1, right? So this is 1 1.
So it will be 0.
So -1 1, and this is 1 1. This is -1 1. X2 is 1 minus 1. -1 1. X3 is -1 0.
So first one is not changing.
-1 0. So this is -1 1. This is still 0.
0. Yeah.
This is -1 minus 1.
Minus.
So this is also correctly classified.
Yes, right.
This is 1. So now this is something that we have to look for. Like x2 need to be updated, right?
Correct.
So now I will do for x3. So x3, which is -1 1 transpose. Now if I have to do W2, which is W1 plus x3 y3, right?
Right.
So W1, we got it to be -1 1.
1 and x3 W3 is
-1 1, and it is
-1, right? So
right?
plus 1, plus 1 minus
1 plus 1 0. 1 minus 1 is it?
0 0.
-1 plus 1 0. 1 minus 0 0 we got. Okay.
So you started with 0 0, or you come back to 0 0?
Back to 0 0. So again, what will happen? Like we start with, if we take this to be 0 0, again this will not correctly classify this, and again we'll keep on repeating.
So this is oscillating.
Yeah, this is not converging.
But if you look at geometrically, it seems like there should be a line between these two reds and one blue. There should be a line which should be linearly separating the two domains.
Yeah. So see, this is let's say this is the W that I can take.
Right.
Oh no, not this.
No. Say any angle, say 45 degree or something like that. So it will differentiate. Yeah, it will differentiate.
Okay.
So why it is not coming through this calculation? Yeah, something like that. Yeah, right. So it will do. So this, why this is not coming in my calculation while doing this initialization? That means initialization is not 0 0 is not right. We have to think about different initialization.
No, initialization is 0 0 only.
But then geometrically, it is very much evident that we should be able to separate it linearly. But while doing a perceptron with this calculation, it is not coming. It is oscillating.
Right.
We can do we can't do if W transpose X will be on the negative side, negative class. Then
I'm sorry, not.
If we consider
Ma'am, can we say
Yeah, what can you repeat?
can we say that this situation is happening only because we have assumed that W transpose X greater than equal to 0, and this situation this assumption is responsible for that, because equal to 0 creating the problem, equal to 0 equal to
But
0.
that is a rule. That is a rule. Right
Yeah,
from the beginning, W transpose X should be greater than or equal to 0.
yeah,
That you have mentioned in the
yeah,
right in the beginning.
this is the
So if
root
you
cause.
challenge that,
What
itself, W transpose X greater than or equal to 0, then you are challenging perceptron itself.
Yeah, of
So
course,
you cannot,
because
if you cannot write W transpose X greater than or equal to 0, that means your assumption is wrong.
yeah, that's why I also understand that this perceptor is also always not converge. If you do not
Yeah.
choose
So
the
geometrically, it looks like it should converge.
yeah,
But if
yeah,
you
but
calculate in this manner,
That's
it will not converge.
correct.
it will not converge. That's why the assumption came the separability. I think so, because this separability came the equal to 0 removed. Right? Am I right, sir?
So that's why I'm saying that. Then what? Then 0, 0, is not the right approach, or what should you do in that case?
No, I mean,
Uh,
perceptron algorithm, like, I mean, 0, 0 is something from where you, like, that from where you start.
yeah,
So that algorithm itself does not have a problem here.
Yeah, but ideally speaking, since whatever initialization you do, it can have a number of runs might increase, but ultimately you will converge. But this particular case, it is not converging. So that's
and
my question.
Not
to refine this case, we got further separability. I think so.
So that is the question. Why it is not geometrically it is separating? There is a linear separation, whereas while doing the calculation through this assumption, it is not separating.
And the second question relating to this, because due to this only, we say that perceptron is
okay.
always converging.
Okay, all right. So, see, this is the figure. Last time I made it wrong. I mean, this is the 45-degree that we have, right?
Yeah.
So what we are seeing here is that this point is exactly on the margin, right? On the right.
Yeah, this is the case.
Yeah. So this is a problem here.
No, and we can take a line parallel to this, na? Let us take a line parallel to this, having some x and y intercept. That will be separating it. Let us take a point, say, yeah, something like that, or something
Yeah.
slightly above.
There
That
are
also separating.
yeah.
There should be some line. What I'm saying is there should be a line which should be linearly separating, which is evident from the graph, from this geometry, but it is not coming through the perceptron algorithm.
Yeah. So it is not that there is only one particular W that can linearly separate this data set, right? There can be many W's.
Many W's will be there.
Which can linearly separate this data set. Now, which W should be ideal here is the thing.
Actually, this question is solved by taking an assumption, which that's the reason I have given you this example. I think which Dishant was raising the same point. If this will converge, if you given in the beginning, if you give a condition W transpose X, if it is less than 0, if it is it should be -1. If you put that condition, it will converge.
If you put that condition, it converge.
It will converge to 1, 2.
Okay.
That's the question. Why should I put that condition? If I put that as a condition, then it converges.
Okay.
But
so W transpose XY greater than or equal to 0 is misclassification. Sorry, less than or equal to 0 is misclassification. If you use that concept,
you do W transpose XI.
XI, YI, sign of XY is less than or equal to 0 is misclassification.
Yeah, okay.
If you put that, then only it will converge to a point, I think, something like 1, 2 or something like that. So that's my question, what should I do in this situation? Should I put the answer as oscillating? Should I, look for, some other, basic? I'm just questioning my basics.
Okay.
So whether in the beginning we have put W transpose XY greater than or equal to 0 is right, or I should consider this.
Okay. No, like if we talk directly from what we have done in the lecture and from the question point of perspective, solving question point of perspective, you should write this is not converging.
Yeah, right. That's what
Right?
I'm asking.
Yeah, you should write it is not converging.
In the lecture
But
also,
in
sir has given example
Based on this,
which
based
was
on this.
but
converting.
there is no option. It is not converging or oscillating in the question, and it is one of the POIQ question. I think Dishant can tell which year is that, Dishant. This POIQ.
This is 13 April. That question, sir, which
Yeah, this
is
question which I am discussing, the same which you
uh,
raised, Dishant.
it is the 10th question.
Someone
Yeah.
has
Jo
put a
yes,
in
yes.
the
Joydev has
that
placed his
that
link
question.
in the chat box.
Which term is it? Which term is it
It
from?
is your previous term, Jan term, I think.
Okay, Jan term.
Yeah, Jan term.
Tell me the question number.
Question 10.
Okay.
This was the question. Yeah.
So what is the answer given for this?
I
1,
think
2, is
1,
it?
2 is the answer, no, Dishant? 1, 2 is
Yeah.
the answer, Dishant?
1, 2.
Yeah, 1 comma.
Yeah, 1, 2.
1
1,
comma.
2, and last second.
Second last, is it?
Yeah.
Yeah, but 1, 2, I am not getting 1, 2. I have tried.
No, Jadav, you will get 2 if you take the assumption. No? If you take your assumption, change the assumption W transpose X less than equal to 0 is misclassified, you will get this answer. 1.
Okay, so was that mentioned in the question that this is
No,
assumption?
it was not. That's my question. It was
Okay.
not mentioned in the question, but if you solve in this way, you will get the answer as 1, 2. Otherwise, if you solve in the normal traditional way, what you have mentioned, you will see it is oscillating, it is not converging.
Yeah, we
So
just
there is no
yeah,
option given also.
right.
No, but I tried by W transpose Xi greater than equal to 0. It gave me the answer 1, 2.
It did. So what did we do wrong here?
No, what you were saying, Dishant?
I am saying I tried by
Is
W
the data
transpose
set
Xi
correct?
greater than equal to 0. It gives me answer 1,
Is
2.
is what
No,
I have
how you
written
get 1, 2?
correct?
Just tell me.
Yes,
You cannot get
ma'am.
answer
The
with this
data
assumption.
set was correct.
I solved it previously, but it gave
0,
me
1
answer 1,
minus
2.
1.
Yeah.
No, you tell me now how you can solve that. You'll get 1, 2. Tell me. We are solving here now. You can see the screen.
Let's see. You can see the screen. Yeah, correct. So
Yeah.
this is okay, right? This is correct. I
This
hope
is
I'm not
correct.
making
Yeah.
a mistake. Then x2, there is a mistake happening. So x2, which is 1 minus 1.
Correct.
Now that will be, so 1 minus 1, but the sign is minus 1 here. So that will be 0, 0, minus 1, 1. This is also correct, right? So now my W1 is minus 1, 1. So I'll check minus 1, 1 for 1, 1, minus 1, 1 for 1 minus 1, minus 1, 1 for minus 1, 0. Right? So in this case, I get minus 1, 1, which is minus 1 plus 1, which is 0. This is correct. So minus 1, which is minus 2, which is also correct. And 1 here. So this is making a mistake. This is also fine.
Yeah, okay.
Okay. Now x3 is okay. X3, I've written wrong. X3 is minus 1, 0.
Yeah, at the fifth phi update, it get
Minus 1, 0. This is a problem. I noticed it. Okay. So minus 1, 0 is x3. That is where we are going wrong. So minus 1, 0 is x3. So now minus 1 plus 1, which is 0, 1. This is 1, 0, 1 we have.
0, 1.
Okay. So W2 is 0, 1. This is also correct. So if I have to check for sign of W2 transpose X1, W2 transpose X2, W2 transpose X3, right? So
Yeah.
W2 is 0, 1, and my data point was 1, 1. This is 0, 1, and it was, I think, minus 1, 1, I guess.
No. 1 minus
1. 1 minus 1, right? And this is 0, 1.
minus 1, 0.
Right? So this is again correct, right? This is 0, minus 1. So this is minus 1. And this is 0, 0. So again, it is making a mistake in x3 only.
Hmm.
This is correct. This is correct.
Earlier also made a mistake in 3. Now it is also making a mistake in 3.
So now we will. So W3 will get what? W2 plus x3 by 3. So this is correct, right? I am not making a mistake.
No,
Yeah.
it should be W3 X3. Yeah, W2 plus X3 X3 by 3. Right?
Yeah, correct.
Right.
So W2 is 0, 1.
0, 1.
This is minus 1, 0. Y3 is what? Y3 is minus 1.
Minus 1.
1, 0. Okay.
So this is 1.
And
This is
1.
1.
Yeah.
1, 1.
Now if I take 1, 1, let's do it geometrically maybe. So if I take 1, 1, then I know again it will make a mistake with respect to
Yeah, the
my
red one. Yes,
X2.
correct.
With respect to x2, right? So I will do now W4, which is W3, which is 1, 1, plus the 1 minus 1 minus, right? So 1 minus 1 is 0. And this is 2.
2.
Right? So if I look at 0, comma 2, so where is 0, comma 2? So 0, 2. Sorry, this one.
Well,
So
it will
now
not.
mistake with respect to x3,
Yeah,
right? So now it will make mistake with
it
x3.
will once again make mistake.
Yeah, so W5 is going to be 0, 2 plus x3 is minus 1, 0. Oh, sorry, not x3, x2.
X1, no?
X3 only, X3 only.
X3 is making mistake. So we'll take only X3.
Yeah. So what do we get? We get 1 and 2.
Yeah.
Now let's see with 1 and 2. So you have 1 and 2. Something like this. And I can see that this will clearly separate. I can check. This is geometrically.
I think
This will fine.
Now if I check this, so 1, 2. Now do 1, 2. This is, I know, going to be positive. 1, 2, 1 minus 1. This is 1 minus 2, which is minus 1. So this is also correct.
Minus 1, okay.
1, 2, minus 1, 0, which is minus 1, which is also correct.
Hmm.
So this is, so W perceptron, what do we get is 1,
1, 2.
1, 2.
It is converging at so it is after 5 iterations it is converging.
Yeah, so you don't have to really, I mean, geometrically you can check these. You don't have to do it manually. If you get a sense that this is happening,
Yeah,
then
you can draw it and you can understand geometrically whether it is.
it just be careful with the distance, all this distance, right? Then it shouldn't be a problem.
Before checking, first we draw the points, then we start just by.
Yeah, then you start, yeah. So
Right.
here the problem happened because we took the problem with the x3, but we were writing x2, and that's why it was coming off with 0. Okay, I hope this is
Sure.
clear.
Just show the last part, madam. Just
Yeah,
W. Yeah, that's the last part. Yes, right. W4, 5, 6. It was taking long time.
Okay,
See.
all right.
We can directly put the value of W by taking the options, and then we can check, right? No?
What?
We can take directly the options also, no, to check, right? No? Is it possible in the option the more than one W? Right?
Option.
It is possible, no? More than one W can also be there. Is it possible?
See, but Perceptron will give you a W, right? It cannot be more than that.
Okay.
So yeah, I mean, if you look at the first four option, maybe you just in the picture you plot those four W's and
Yeah,
see.
let us plot all the four options, madam. I think it's a good
Yeah,
question.
that's why I'm questioning, because
Yeah, I think
it is
Srikanth
very
is
difficult.
asking a good
Yeah.
question.
Just put the
So out of
W.
these four options, let
Yeah.
us put it.
Whether
put
we
it
can
in-
we can make a trick to
Yes,
answer
in the
check.
graph, let us put
Yeah,
that.
please.
Drawing this figure. Just tell me someone tell me what is the point, okay?
Yeah, yeah.
What is the first W?
First one is 2,
1, 1.
1. Yeah, 1, 2. Now 1, 2.
First one is 1,
1,
2.
1.
1, 2.
And 2.
The first one is 1, 2.
It is, yes, right. This is doing it.
Mhm.
The second option is
W1.
Tell me
1, 2.
this.
Second option is how? What is that, Disha?
1, 1.
1, 1. Okay. Let us try 1, 1.
Okay, 1, 1. 1,
See,
1,
1 cannot be because it is the line in a point itself. So
Yeah,
it
it
cannot
will.
have 1.
0, 2,
0,
right?
2. And 0, 1.
And 0, 1.
Yeah.
0, 1. So see, you can look at these
It
four,
cannot have.
and of course, this like this is W2, this is W4, this is W3. I can look at W2, W3, W4, and can easily discard that. Okay, this is not going to linearly separate. I mean, the perceptron will not give this a solution.
When any of the points lie on the W,
Okay.
it will keep converging.
It will
Here,
not. It will not be.
so if
Right?
it converge, it may not converge. If it
Yeah,
lies,
may not converge. So we have to start trying for that point of W, which
So
is not lying on the data point. Right now?
no. So see, I mean, if your W, if your data set is exactly on that decision boundary, it may converge, it may not converge. So what is something that you will check in that case for all these W is that you will check for sign, right? You will check for sign of these things for all these W you check and see if they're making any mistake. So the very first thing you can, so looking at all these four options, they all are linearly separating, right? But from here, I cannot say that this is something that my perceptron algorithm will select. This is W converge, right? So the next thing to do would be you check the signs. So for W2, if you check the signs will not match. W3 it will not match, and so on, right? So only for W1 it is matching.
Matching, correct.
Okay. Yes.
Since these are, in R2 we can do this, but it is within RD, then we cannot do such calculations.
Yeah, in R2 can only by drawing we can guess something, otherwise
It is not possible.
We cannot do on.
You cannot do. That's the reason of this algorithm.
Yeah, this is learning. For the learning, we understand from this and we apply algorithm for the other dimensions, right?
Correct. In 2-dimensional, geometrically, we can understand. In higher dimensions, we can understand it should be a plane. It's a very,
That is why the name is Perceptron. Our perception will work. Correct. Thank you. Thank you, ma'am. Let us proceed.
You can go to the next.
All right, let's move to the next part. So, yeah, so we saw about the mistake, we saw this problem also. I hope that cleared a lot of doubts. So, okay, so this was, when we looked at this question, we can say that there is some further assumption that my perceptron makes, right? And what are these assumptions? So, we can write it as further assumptions. So the very first assumption is that only linear separability is not enough. It should be linear separable with some gamma margin, right? And when we say linear separable with some gamma margin, what we mean is like for the data set D that you have, what should follow is that there should exist some W which belong to RD such that my W star transpose Xi, W star transpose Xi, Yi should be greater than equal to gamma for every I, right? And gamma should be positive. So this is the linear separability condition. So if this is my W, this is my W, this is my decision boundary. So this is the margin that we have for the data set. Okay.
There exists some W.
There exists.
There exists some W star belonging to RD. What does it mean? Some W means at least one W or more than one W. It can exist, na?
Please, at least one. There exists a W.
At least one, right?
There exists a W.
Yeah.
Okay. Like in Perceptron, like there will exist a W such that this will hold.
RW is only one or more than one also.
It can be more than one also.
Yeah. It means there is some W means it can be
Some
more than
W,
one.
there
Correct.
exists some W.
Got it, ma'am. Yes.
So what is this line? This line is set of all X such that my W transpose X is equal to 0.
0.
Is set of all X such that W transpose W star. So sorry, W star transpose X is equal to gamma.
Yeah.
This is set of all X such that W star transpose X is equal to minus gamma. Okay. So this is linear separability assumption. Now there are two more additional assumptions that we make. So the another assumption is that your length of the data point, right? It should be strictly less than equal to R, some radius, where R is positive, and it should happen for every I in your data set. So what we mean by saying that is that if you have these data set with you, whatever the length is, the maximum length will be centered in, all these data set will be, the length will be inside a circle of radius R. Okay, this is what it means. Be some bit of figure. So yeah. Okay. So the length of all these xi, so xi's can be bounded in a circle of radius R is what we are trying to say. And the third assumption we make.
In this case, the value of R is the norm of the highest xi, is it?
Yes.
Right, na? We can say, na, like that.
You can say, yeah.
Okay.
And the length of W star, can you mute? Yeah. So the length of W star has to.
ये तो 150 वाला master काटा ने.
Can you mute yourself?
1.25.
Yeah, thank you. So these are three assumptions that we make for the Perceptron algorithm. Now, when we
I'm set of data points, suppose set of data points are there and it is given, and for this assumption, can we just take the highest X and take the norm and say that the value of capital R is this? Is it so, no?
Yeah, we can. I mean, see, all is it saying is that my xi is inside this R. It can be greater than also.
Yeah, it can. It can be greater than also. Yeah. It can be greater than also. Correct. Okay. Thank you. The bound that R will be the bound. The highest value of X will be the bound, right?
Yes.
Yeah. Okay. Lower bound. Okay. Thank you.
So, all right. So when we are talking about the Perceptron algorithm and its convergence, so what we had also one result that we saw is that the perceptron algorithm converges. Perceptron converges, and the number of mistakes is bounded above by r square by gamma square, where r is the radius in which is the radius of the circle in which all the data set is enclosed, and gamma is the length of the margin. So the number of mistakes that the perceptron algorithm makes is upper bounded by this r square by gamma square term. So since it's a finite number, we can say that the perceptron algorithm will converge. Okay, so this is one result from perceptron. And what is, like, when we were proving it, we had also seen that this WL norm, I mean length of WL, is bounded above by L r square and L square gamma square. Let's see this. Okay. All right. So what did we see in perceptron? So we saw that here the goal was to find out a decision boundary that clearly separates the data set in two classes. And this is the assumption that we had made on the data set, like probability of y equal 1 given x should be 1 if this is positive and 0 otherwise. And the second was linear separability assumption. And
ma'am, one thing that this is the W L plus 1 norm square or L norm square?
Here it doesn't matter. Okay, here it doesn't matter because, see, even if you write WL plus 1, what you're going to get is WL plus 1 square less than equal to L plus 1 R square L plus 1 square gamma square, right?
No, but in the lecture, L plus 1 is WL plus 1 gamma square is less than L R square and it is greater than L gamma square, L square gamma square. In the lecture?
But I had told, right, that there is a mistake in the proof.
Yeah, last time you told me, but I could not know where it is the correction and how it came.
You go back and check in the session. I given a correct proof of that. So there was a mistake in there.
Okay, in the lecture there is a mistake.
During the proof, but it doesn't matter much because at the end all we are getting is the number of, like, there in that case, the number of mistakes that we had taken was L.
Yeah.
Right.
Yeah.
But,
L number of mistakes.
Right.
Yeah.
So number of mistakes. So all that we want is number of mistakes that your algorithm will make is bounded above by r square by gamma square.
Yeah. Okay. That will be the same. Only this value will vary. Okay. Okay.
Right.
Okay. Good. Okay. I will see the. You have given somewhere. Okay.
Yeah.
Sure. I have to search. Okay.
Okay.
But we can directly apply this formula. No problem. Right. L is equal to r square upon gamma square is okay. That is universal. Right?
You can apply this.
Okay.
All right. So that was about perceptron. Now let's move.
Slightly go up, madam, and just one question. Yeah. In some of the no, just go down. No, I'm doing down. Yeah. In some of the questions, it was written as L plus 1. Should I consider L plus 1 to be L or what? In the lecture.
Which question it is?
This one, that boundary, upper and lower boundary. It is also mentioned that L plus 1 gamma square and L plus 1 R square. So should that be L or L plus 1?
You're saying WL plus 1. This?
It is, yes. L plus 1 R square. Everywhere it is mentioned as L plus 1. So, which one is more appropriate,
I mean, see, L, if I'm writing L, it means this is the number of mistakes my algorithm has made. L number of mistakes, right? If I'm writing the number of mistakes as L, right? So I'm saying this L is less than equal to R square by gamma square, correct? If I'm writing number of mistakes to be L plus 1, then this is, I will say L plus 1 is less than equal to R square by gamma square. So what you can also
yes, for question, if the question is given, should we consider L plus 1 or L? That's the question.
where this part, this you're talking about this part?
In the exams, if number of mistakes are asked, should I consider?
Yeah, this is
No,
the right
this
question.
is
This is
L
the right
plus
question.
Number of mistakes, if number of mistakes is asked, all you need is R square by gamma square.
No,
No,
ma'am.
in
No,
that
no. Number of mistakes is L. Okay. R square by gamma square is 5. Then the
Okay, okay.
value of L will be 4 or value of L will be 5. This is the question.
yeah,
Okay,
that's the question.
tell again. Tell again. If number of L, if L is
No, if say R is given and gamma is given, say R said, let us take R to be.
Take any value of R and gamma.
Yeah, let us take two values of R
value
and
of R and gamma. Okay.
yes. So gamma is 2 and R is say 4.
That's not needed. Okay. Tell me about L.
What should be L?
No.
We want to find the value of L if
Just
R and gamma is given.
R square by gamma square, you're saying?
No, it should be R divided by gamma square minus 1 or R square divided by gamma square. That's the question.
No, but that depends on what is L you have taken, no? I mean, how many number of mistakes you tell me?
Yeah, how many number of mistakes it will make? It will make R by gamma square minus 1 or R by gamma square?
R by gamma square.
But in this formula you have written L plus 1 is less than or equal to R square by gamma square.
L plus 1 is the number of mistake now.
So that's what I'm saying. So in that case, both are same. So L or L plus 1, whatever you take, the number of mistakes is...
Number of mistakes is bounded over by R square by gamma square.
That's why. So L plus 1 is equal to L. Both are same.
I mean, if I'm taking...
In the lecture it is done with L plus 1, but we can also do it L. So that's what I'm saying. Both are same.
So in when we're looking at the proof in the lecture,
yeah, right.
There was a one mistake over there, right? So I mean, it should be L plus 1 R square, but in the lecture it was written L R square. Or the other ways also in the second part. So okay, just to avoid this, maybe what you can do is do you have Karthik's note?
This number of mistakes will vary, ma'am. Every time when we change the value of a perceptron, when you run the algorithm, every time the number of mistakes will vary. Sometimes it will be less, sometimes it will be more. Okay, it will depend on that also. So
no,
we cannot.
The question is not about that, right? Here the question is about this, correct? This is the question that you're asking.
Yeah.
Yeah, right.
Here, see, if I'm writing this, let's say this, I'm saying number of mistakes my algorithm has made is L. Okay? And if I'm writing this, I'm saying number of mistakes my algorithm has made is L plus 1. That's all.
Okay, ma'am. This can be solved if R and R is given.
Yeah. Okay.
But then Shrikant, number of mistakes will be always fixed, constant, because
No,
R is
R
and gamma.
For
a given R and given gamma, I is fixed.
Don't go to this. Go to the algorithm. At the time of algorithm, the L mistakes happens if you take some value W. Then L number of mistakes happens. If you take another W, suppose a mistakes comes. Suppose 5 mistakes comes. Okay, and you start with the first mistake. Okay, got my point. Just running the algorithm. With the first, now 6 mistakes comes. Then again, you got my point. What I'm telling.
Yeah, I got your point.
Yeah,
but I'm saying R is fixed, na? Is R variable or
R is also not fixed, na? Because R is having a bound only.
No, R is fixed.
R is fixed, na?
R
The radius is
fixed.
And gamma is also fixed, na?
Correct.
Yeah,
Then
yeah.
how can L change? L should not change. R and gamma are fixed.
And that, if that is not a problem, see,
I'm saying number of mistake in that case in any algorithm
it
with
is,
knowing.
let's say r square by gamma square, they are fixed. They are coming out to be, let's say, 10. Suppose this value is 10. Okay. So all it is saying is that my number of mistakes
Is less than equal to 10.
iteration
Yes.
can be less
It's an
than equal
inequality.
To 10, yes.
10, right?
Maximum, it's upper bound.
Yeah.
Upper bound
Yes.
is 10. It cannot make more
10.
than 10 mistakes.
Correct, correct.
Okay.
That is what we are
That's what
telling.
I'm saying, yeah.
Yes. Right. That is what we
So
are
what I was telling is that, now suppose there are 3 mistakes in in the first round. There are 3 mistakes, right?
Yes, yes.
In the second round, suppose we encountered with a mistake, then we will run the algorithm. Then W will change, right? And then W will change. The may the algorithm always reduce the number of mistakes, or it may go to 10 also. This was the previous question also. Suppose 3 mistakes, okay, in the first round. So whether in the second round, it will go to 4 also, or it will go always below 3. Because we have not checked on the number of datas, because we are just learning the principles only. So I think because the number of mistakes will always change, L will change. It will be
Yeah,
always below 10, but it will maybe 3, maybe 2, maybe 5. In every round, it
and
will.
that is correct.
Right, na, ma'am? This is
Yeah, that is right. That is right.
Yeah. This is
It
the
will-
That is
situation.
correct. That is correct.
That is why L and L plus 1 both are correct. Any number of mistakes can happen, but it will be always less than 10. Am I right?
Less than equal to 10.
Yes.
It can be 10 also.
Yeah.
Less than equal to 10. Yeah.
Yeah.
Okay.
Okay.
So all this is saying is that the bound will be less than equal to r square by gamma square. That's all.
Okay, ma'am. Okay, ma'am. Clear.
Yeah, please carry on, please.
Carry on.
All right. So let's move to the next topic. So now we have logistic regression. So, okay. So, what if the data set, like in Perceptron, the assumption that we have made that it is linearly separable, right? And it will take the value 1, probability y is equal to 1 given x. Will take the value 1 if W transpose x is greater than equal to 0, else it will take 0, right? So, can we relax this assumption? And like in case if we have a data set which is not possible to be linearly separated, then how do we can we come up with some different kind of algorithm in that case? So in logistic regression, the idea is that so whatever W we choose, right? And let's say if a particular W, let's say this is my W, and this is my decision boundary. Suppose I have a data set over here, and I have a data set over here, and let's say I have a data set on this side and one on this side. So what we would want is the more far, the more this distance is, this W transpose, the more this distance is, the higher probability it should be that this point x2 will belong to class 1, right? So in some way, we want to associate probabilities to each of these data points that we have. And every data point has, we are allowing every data point to take the label as either 1 or -1. But there will be some probability associated with it. So higher the probability, higher the chance that this data point belongs to a particular class. So what do we do for this? We define a sigmoid function, right? So this function is g of z to be 1
upon
1 plus e to the power minus z.
Right.
minus,
Yeah,
right?
right.
And this
Which
is
is W transpose x1, x and y1.
this is sigmoid function.
Yes, yes.
And
Sigma
now if we take z to be
W transpose x and y1.
So
X and Y1 also, no, madam?
what?
X and Y, both. You have to put W transpose X and Y.
X
That
and Y.
way, yeah, Xi and Yi. W transpose Xi, Yi.
No. Z is W transpose X.
No, only W transpose X is used.
Why Yi is not there?
Z is W transpose X, and the value is G of W transpose X.
Yi is not there, you're sure?
No, it is not there.
Y is not there. So Z you take it to be W transpose X.
Yeah.
What are you trying to do? We are see we wanted probability Y is equal to 1 given X to be 1 if
If W transpose X is greater, yeah.
zero.
And this W transpose X is Z. We assumed it is Z.
Take this to be Z.
Right, no?
Yes. So if you plot this, sigmoid function, so this is my Z and this is my Z of Z, and this takes the value between 0 to 1, right? This sigmoid function.
Yeah.
So you have a function which looks like this S-shaped. Correct? So this is 0.5. So what we can say from here is that G of 0 is going to be 0.5. Right? So saying that, meaning that if you have W transpose X to be 0, which is Z, so this point has an equal chance of going to any of the class.
Yeah.
And the higher the Z is, so as Z will tend to infinity, my G of Z will tend to 1. Right?
And minus infinity tends to 0.
Correct. So and as Z tend to minus infinity,
Infinity tends to Z tends to 0.
G of Z tends to be 0. Right? So and which makes sense also. Right? So based on that, we provide some probability to each of these data points. So what are we trying to model here? We have probability of Y to be 1 given X now is nothing but Z of W transpose X, right? And this is equal to 1 upon 1 plus e to the power
minus W transpose X.
Right? So if you are given any data set, if I am given some X test, and you have to find out what class this P can go to, you find this probability, and let's call this some small p. You find this probability and see how much is it, right? And let's say in the questionnaire, maybe it is given that if probability is greater than this, I will assign it to, maybe I can say if P is greater than 0.7, I will classify this as class 1. Otherwise, I will classify it as Z. Right? Okay, this is how we can predict for in case of logistic regression.
What did you wrote, ma'am? Probability greater than 0 plus.
Where?
What is
No,
this?
no. This is 0.7, I will think.
Yeah. 0.7. Okay. It is greater than 0. Then yeah.
Okay.
So how this threshold is arrived at? P greater than 0.7 is 1.
This is something that you have taken. I mean, this is not coming from the algorithm. This is something that you have provided.
How actually it is done? That's what I'm asking. It should be 0.6 or 0.7 or 0.8. How it is arrived at? That assumption of P greater than 0.7, it should be 1.
0.5, we can ideally take it as 1, but maybe depending on the kind of problem statement, maybe you want to put your threshold to be higher.
We can calculate the value, no, ma'am.
So
1 upon
there is an error also.
W transpose X. The value of that will be the threshold now.
No, that will be not the threshold is this 0.7. You cannot arrive there. You can also decide based on this whether it should be what do you call? You get it 0.7 or less than 0.7, the probability. But you cannot set this threshold. That's what I'm asking. How it is decided, this threshold?
Yeah.
So is there any any approach to arrive at this threshold, or how it is taken? How does the algorithm takes this threshold value? We put it as a
Not specific to like, there's no such specific method. You can just test it out and see it, like maybe something like trial and error.
because ideally speaking, if you put 0.7, your the error what will happen is basically you are there's something which is more than 0.5, so 0.55 or 0.6. They may be good, but you are you're omitting it or you're not considering it. So there are chances of some good ones rejected because you're putting your threshold very high, or maybe you can put your threshold low. So then there also error chances will be high. So
Yeah,
how do
but
you optimize that? It's almost like optimization.
that will depend on the data set. The data set you have, kind of, and decide this. Okay. All right. Um, so the W that we have for this W, we can estimate it using the ML estimate, right? So when we tried ML estimate, we had seen that there was no closed form solution, right? So no closed form solution. Okay. So what we switched to the optimization technique, and which that was gradient descent algorithm. So
What
using
do you
this
mean by this?
optimization technique, we
What do you
can.
mean by no closed form solution? Actually, your
So
voice is breaking.
you
So
saw this. Is it clear now?
Yeah,
Is it
some
better?
now it is okay.
it is better
Okay.
now. Yes, better. Yeah, tell me.
See, for example, in this case, I will write the likelihood. So L of W given
Breaking.
X, this turns out to be sum over 1 minus yi minus of W transpose xi minus of log 1 plus e to the power minus W transpose xi. Okay, I is varying from 1 to
Are you writing
20.
something on the board? But it
Yeah,
is not
something
visible.
breaking.
Something
Yeah,
breaking,
some
and its screen is not
Uh,
also.
writing, right? You can
Yeah, now it is okay. Lagging.
let
It is
me
Now it is.
share. It is
okay.
visible.
Yeah, visible. It is lagging. Is it lagging
It's visible
only?
now. Yeah, right.
Okay. Okay. So if this is your likelihood, now what should be your next step? We will substitute it to 0.
How do you get this one, madam? This line 1 minus y and minus W transpose x1 minus log.
I have skipped all the calculation and I directly wrote
Sure.
the
You have
final.
skipped all the calculation.
Yeah, log of that.
Yeah.
No
Okay.
problem. No problem. No problem.
Find the log, like find the likelihood. You know how to find the
Yeah,
likelihood,
okay.
right?
We have just
This,
you have just directly written
now,
the
You have written the direct final formula.
likelihood function, right? Objective function.
yes. Yeah. So now what is, if this is the likelihood, what we would want?
Maximum max sub W.
So
We
W
need
star
maximum W.
is going to be the W that gives you the maximum value of the likelihood. But
So you take a
how
derivative
will
with
you
respect
solve
to
this?
W. We'll take a derivative with respect to W.
Right. And then we have to equate it to 0.
Yeah.
Right?
Yeah.
So what will you get?
Minus 1 minus y1 minus x1 into minus x1.
Minus
Yeah.
4.
Yeah.
correct?
Yes.
Then
Minus 1 by whatever.
log of
1 by something, that entire thing.
We will get minus e to the power minus w transpose xi divided by 1
this,
plus
which
e to
is
the power.
minus
This minus of 1 by 1 plus e to the power minus
power minus
transpose
w
x1. Yes.
Yeah.
Into minus w
minus xi.
into minus xi, minus xy.
Minus x1.
So that will
This is
become plus xi. Yeah.
what is
The voice is breaking.
Yeah. Network is lagging, so it is
this
coming.
is my
Clear.
xi.
Correct.
Give me a minute. Wait.
Okay, ma'am. Okay. Restart, ma'am. Something wrong.
The voice is continuously breaking.
Restart, ma'am. It is better. Reconnect.
Okay.
Today, ma'am,
Is
we'll
it better?
do week 9 and week 10 both, na, ma'am. Week 9, week 10, na, both, na.
Both. Is it better
Both.
now?
Yeah, it is better.
Right. So
It's better. It's better.
you take the derivative. You take the derivative, and so L of W is what we get is sum over xi, yi.
Minus.
We can write this as minimization problem.
Yeah, ma'am. Right. 1 plus e to the minus w transpose
Yes.
xi. Yeah, this
Minimize
is
this one.
correct.
Minimize.
Right.
Yeah.
Now, see, you have this. Now, what do you have to do? You have to take it to substitute it to 0, right?
Yeah, right.
So, and you have to find what? You have to find your
Gradient, na, ma'am, first.
you have to find W.
You have to find W star.
You have to find W star, correct?
Right.
So you have xi yi summation, right?
Is equal
1
to
to n minus summation xi 1 by 1 plus e to the power minus w transpose xi, right? Now you substitute this to 0.
It becomes 0.
So basically, this is this. So now, see, the challenge here is in finding this W, right?
Yeah, right.
Okay. So that's why we are switching to this gradient ascent algorithm. So you won't be able to find some nice W, which you can write, which you can write here. So that's why we are moving to, even when you like when you would have seen the CM algorithm. Even there, when we're doing the GMM and we're doing the ML estimation, it was we were not able to get some. I think in that case it was it could be something, right? W, let's say. So there also we're not able to find it. So we moved to the EM algorithm part. We solved it using the EM algorithm, that GMM. So similarly here, logistic, in place of logistic, they are doing it with if you're finding W using the gradient ascent algorithm.
It is why it is gradient ascent, no, why not gradient descent?
So you move in gradient descent. What do? You move in the so gradient. It is a minimization problem, right? In when you're writing gradient, like for example, regression problem, you want to minimize the error. You use the gradient descent, so you're moving in the negative direction. Now here, you're trying to maximize this.
Okay. So that's why gradient ascent.
The maximum, I mean, positive direction here.
Okay. So that's why the formula changes to
Formula changes to
1
very.
plus
So in
eta.
place of
Instead of minus,
in
it should
place
be
of
plus
minus
eta.
theta, you
It
guess
should be plus
plus
eta.
theta. That's
Correct.
the only difference.
Correct. That is a very important thing,
We want to maximize the objective function or the value of W.
What?
We want the maximum W or the maximum value of the objective function. What we are maximizing here?
We want to optimize by finding that W star which will maximize the objective function.
Objective function. We want the maximum value of the objective
Yes,
function.
it is the value of W star.
W. Okay.
Objective function, which in this case is the log likelihood.
Log likelihood.
Log likelihood. Yeah.
Right.
Okay.
Right.
Okay. So this is how we can use the logistic regression. So you can find the probabilities associated with each point, and that is given by 1 plus e to the power minus W transpose xi. Right. So now moving forward to the next algorithm, we have support vector machine.
So what we got W star, ma'am, here? Go back, please.
Mm-hmm.
This. What is the value of W star here? What we got here?
So W star we will get using the gradient ascent algorithm. So see,
WT plus 1 is WT plus eta t.
Plus eta t into
gradient of this
gradient of LW.
What is this? WT plus 1 is WT plus eta t.
Gradient of yes.
Log of L of W.
And this L of W is xi, summation of xi into yi.
This, right? We found this here.
Correct. It is already defined.
Right? So
Okay.
what
is the use of this summation of yi is equal to summation?
Listen to me first.
Yeah, please.
So at any iteration, WT plus 1 is WT plus some eta, some step size. And if you see this was nothing but some linear combination of data point. This is yi, which is a scalar, and this is also going to be some scalar, right? So in short, I can say that this is the grad of L is nothing but a linear combination of data point.
Yeah.
Right. So it is something like summation xi, summation xi times, let's say, alpha I. Right.
Okay. We assumed the alpha I for that, right?
Same thing we did it for EMM also.
Then kernel comes, right?
Right. So this is just some linear combination of the gradient. So I mean, and this is this is the update truth that you have for gradient ascent, and from using this, you perform this gradient ascent algorithm and you get some W star from here. Now you use this W star in this place, right? So let's say the W star that was learned is maybe if it is one dimension, if W is an R1, maybe let's say W is 2 is something that we get. Then it should be what? It should be 1 plus e to the power minus
minus 2
2x.
2 into x here.
Now let's say my W star was in R2, so let's write it as let's say this is my W star. Then what will we write? Yes, we'll write this as 1 by 1 plus e to the power minus
1 to
x1. Let's call it x. Let's write x as x1 x2. Okay. Or let's not do it here. So what will you write? So W is 1 2.
1 2
W1 x1
into x1 x2.
X2, right? So it can be written as 1 by 1 plus e to the power minus x1 minus x2 x2.
Yeah.
Now let's say W is in R3. The data set is in R3. Let's say it is 1 2 3. Repeat the same thing. Then you will have 1 plus e to the power minus x1 minus 2x2 minus 2x3 3x3. Right?
Just it is a matter of getting the minus W transpose X. This is
just a matter of getting yeah. So if you have to predict, get the probability, you need to know what is the W, and this W will be learned using some optimization algorithm. This learned W is will be given to you, right? And you can easily find it. So how is W found? So we are using this gradient ascent algorithm to find a W, and we have also seen that how this is giving us a like good solution for this logistic regression. Okay. So, for example, like we had seen that if I let's say Wi, if we take it to be 1, right? So if we take Wi to be 1, then what will happen? If we have to, and what is the probability that we have to find? It is probability that yi is equal to 1 given xi, and it is given by 1 plus e to the power minus wt transpose xi. Right?
Yeah.
So if if I take it to be 1, and so if this is 1, this term, which is 1 divided by this is a probability, right? This is going to be greater than equal to 0. Sorry, less than equal to 1. Right? This
Pardon,
term will,
one second, ma'am. What we're telling? Pardon? What you told?
see, if this term, which is 1 divided by 1 plus e to the power minus t transpose xi, if this term is high, and this is what? This is nothing but probability. Probability that yi is equal to 1 given xi.
Yeah.
Right? So if this term is high, and this is also 1, if this is 1, right? If this is 1 and this probability is high, probability that xi, probability yi is equal to 1 given xi, then this alpha I mean the difference between these two would be small.
Is negative.
Will be negative, right?
It will be negative.
So this not negative. I mean this will be less small. All we can say is small, right? This is a probability. This is 1, and what we are saying is that this value is high.
Yeah, small, not negative. It's small because probability will be always less than 1, right?
It would be small. Alpha I would be small, right? So this data point will not. It is not contributing much in your gradient, right? So not much update will happen there if you look at the update rule. But in case if this is small, if your probability is small, right? If this is small, then this whole term would be high, and that point will move to that direction. Right? Those will be the point that will actually affect the gradient.
That means for whatever it is low, it will affect, isn't it?
Yeah, whatever it is low, it will affect. It will affect the gradient, and that is exactly what we want.
So
also
low means the denominator has to be high. That's why it should be e to the power minus instead of minus W transpose.
But it's not about denominator. I mean, it's about probability of phi is equal to 1.
That's what I'm saying. If you go in the other way, denominator has to be, if it is low, means denominator has to be high. Denominator has to high means your W instead of minus W transpose, it should be e to the power plus W transpose xi. That is what the weight we give it to, the ones which are making it.
Yeah.
So how the value of WT plus 1 will affect with this value of probability? Suppose It is
See,
low.
if this is low,
Yeah.
this is, then it is not affecting much our weight.
Yeah,
Right?
it is not affecting much. Correct.
If this is high, it means if there is a big mismatch between these two terms, between the actual y and the predicted y, then there will be a big jump. I mean, a big jump in the W.
Big jump is always increase. It will always increase because positive. This will be positive value only.
It will
Right?
go to the right side basically.
Yeah. Okay. Because we want it to increase
I
the
don't know
value.
whether
Yeah.
it's going to the right side, but I mean, it will go. It will impact more. You can say.
Yeah.
Okay.
That's why when you are making an error, we put e to the power plus wt transpose xi, it will impact more.
Yeah.
We want to correct it actually.
Hmm.
That's the reason it is having a higher weight.
So higher the value of probability, the rate of change
No.
will be more, right? No?
Yes, lower the value of probability. That means yy minus the probability or the entire
Yeah,
piece will
lower
go
the
up.
value of this, it will increase more, right?
Yes. So
Correct.
that the delta LW will be more.
Okay. All right. So you can look at the theory yourself also. I mean,
Yeah.
you can look at these things. All right, if you are interested.
Mhm.
Okay. Let's move to the next topic. So the next topic we have is support vector machine. So in Perceptron, we had seen that there are, I mean, if the data set is linearly separable, we saw this perceptron algorithm converges, right? And there is a bound that we get that the number of mistakes it can make. But I mean, if you have a data set which is linearly separable, I mean, there can be various W, which is the possible solution for that question, right? I mean, if I look at this data set, I mean, this is one W, but maybe there is another W, which is this W star, and this also is doing the job, right? So, which is the ideal W? I mean, which is the W that we should go for? So, like what we would want is that the W that gives you the higher margin, the larger margin is the W that we should prefer, right? Because if any new data set is coming in, now you have a bigger margin to see. So if it will generalize it more well. So we are looking for basically the W which has a higher margin, right? So what is the question here now? Now the question that becomes is
We are looking for the W, which will give the higher margin, gamma, right?
maximum margin, right? Yes. So now the question here is to maximize this margin gamma with respect to, so subject with respect to W and gamma subject to the constraint W transpose xi yi greater than equal to gamma for every I, right? So this is the problem that we want to solve.
This is the constraint, right? That's true.
Yeah. So this is the problem that we want to solve. And what we got is that I am not going to do the maths here because I know we have already done it earlier. So
Yeah.
what we know is that this is equivalent to, so this margin, this is equivalent to maximizing 2 divided by norm of W.
Norm of W square.
Yeah. Subject to the constraint, this W transpose xi ya given less than greater than equal to gamma. Now,
Which is also equal to minimizing norm of W by 2.
Correct. So
Next step.
Yeah. So now this is a maximization problem. So if we want to, like what we can also do is we can write it in the form of minimization problem. So maximizing 2 upon norm of W square is equivalent to minimizing norm of W square by 2. right? So this is equivalent to minimizing norm of W square by
W
2,
square by 2. Correct.
subject to the constraint that W transpose Xi Yi is greater than equal to gamma
Yeah.
for every.
Yeah.
Now this is in SVM, this is a problem that we are trying to solve here now. Okay. So let's see. Write it here again.
Just one question, madam. Actually, should you not write that subject to condition as gamma minus W transpose X1 Y1 greater than less than 0? Because you have to
Yes.
put it in the GW less than
Yeah,
equal to 0
we'll
form.
come to all that. We'll listen first. Okay. We'll come to all that. So this is something that we wanted to minimize, subject to the constraint that W transpose Xi Yi is less than equal to gamma. Okay. So now, if we have like if we have an optimization problem, which is like minimizing some function of W, subject to a constraint G of W less than equal to 0, then what we saw is that maximizing the f of W plus some alpha G of W, which is nothing but Lagrangian, this turns out to be uh, this turns out to be 0 if my G of W is greater than 0, and if G of W is less than equal to 0, this is f of W. So you don't have to remember this. I mean, there's nothing to remember here. So see, this is the Lagrangian, and we want to maximize this Lagrangian. So, and alpha we have taken it to be greater than equal to 0. So just think about it. The problem we have here is to maximize this. Okay. Now, if alpha I take to be positive and G of W is also positive, so this can go to infinity depending on what alpha is or what GW is. So the maximum value it can take is infinity.
Yeah.
But if G of W is less than equal to 0, right? If this is less than equal to 0, I know alpha is positive, so this term is going to be negative.
Correct.
So if this is going to be negative, the maximum, and you have to find the maximum of this whole thing. So the maximum you can take is when alpha G of W is equal to 0.
Yeah.
Right? So the value that you will get is f of W. Alright? So now what your problem becomes is earlier where we wanted to minimize f of W with respect to W such that G of W is less than equal to 0. Now this is equivalent to solving minimization of W, right? And f of W, we can write it as f of W. We can write it as max of alpha
Greater than equal to 0. Yeah.
f of W plus
alpha G of W.
W. Right.
Here,
these
in this equation, ma'am, the max of f of W is separate. Max of alpha greater than equal to 0 is associated. Yeah. It is like that. Alpha is applicable to both, right? Na?
Correct. Yeah.
This is one function, f of W. Yeah. Okay.
F of W plus alpha GW is one function. Okay. So this is my primary problem. Now, in case when we have nice functions, like when my f and g are convex function, then this duality holds, and what we can also say is that this is equivalent to maximizing with respect to alpha positive and minimizing with respect to
W
f
f
of
W
W
plus alpha G W.
alpha GW. Okay. So this is, I mean, this is all that can be done. Now the problem, the original problem that we had was my f of w was now of w square by 2, right? So, and this is my constraint. So now this can be written as w transpose xi yi minus gamma, or minus gamma. So this we are taking it as 1, right? Not gamma and gamma. So okay, so 1 minus w transpose xi yi less than equal
Yeah,
to 0.
1 minus W transpose Xi Y less than equal to 0 in the
Call this
standard form of Lagrangian, right?
now I can write this as g of w, gi of w, right? So now we substitute, just shift these two, and what we can write now is the problem is minimize norm of w square by 2 subject to the constraint that 1 minus w transpose xi yi
Less than equal to gamma.
is less than equal to 0
0
for every I.
for all I.
So you can find the Lagrangian, and then what we will get, what we will get is that here. So this, minimizing this is going to be equivalent to minimizing my w, minimizing with respect to w, and maximizing
Alpha greater than 0.
maximizing this alpha I greater than equal to 0, half of norm square by 2 plus, now see, these are I constraint we have suitable constraint as I. This we can write as GIW. This is sum over I varying from 1 to n, 1 minus alpha I, because for every
Alpha
data
I into G.
let us please do not speak in between, okay? So alpha I
Into 1 minus W transpose X on Y.
Alpha I into G of IW.
So that is 1 minus W transpose X on Y.
alpha I 1 minus W transpose X I.
Yeah.
Right?
Yeah.
This fine. So now this
Just one question. Just madam, can you, if you go slightly up, we have taken gamma as 1 or what? Just slightly up.
Gamma is 1.
Where is there? You have not
assumed gamma is equal to 1.
Assumed to be 1. Correct.
Yeah.
Understood.
So this is my primal problem now, and what we will do is, and we saw that it can also be written as the max min form. So now I can write this as max alpha I will be equal to 0, min over W, and all this whole thing there, right?
Okay.
So now we can solve our dual problem and find our alpha. Find our W. So for some alpha positive, we can find our W, and for that, what do? We take the derivative of this with respect to W and equate it to 0. And the answer, the W that we get, the solution that we get, W star that we get, is nothing but sum over alpha I xi yi.
Right. W star.
Right. This is this for some alpha. Alright. So here alpha I should be positive because this is how we have to find it. My xi is in RD and my yi is in plus minus 1. Alright. So this can also be written as if this is right.
Xi is what? Xi is belongs to
RD.
RD. Okay.
RD.
Yeah, RD. Correct.
Why? Where my X, the matrix X is X1, X2, so on.
Yeah. Correct.
Y is all the diagonal entries, and then alpha 1, alpha 2, so on to alpha n. So this is the W star that we obtain. now for this W star, what we will do is
So what will be the this thing of XY alpha? It will be in the RD. It will be RD or RN. R into RD only. X will be in RD, and Y should be in what? All.
It will be D cross N,
D cross N, and then N cross N. Ultimately, you get what? Yes,
this is N cross N.
N.
This is N cross 1.
Yeah, so you get D cross 1.
You get N cross 1. So overall, you should get D cross 1.
D cross 1.
And see, you don't even have to do this because see, you are finding W, and W is in RD. So this should give you a vector in RD.
RD, right? That is what I'm saying. So it will give you a vector in RD.
Yeah. Okay. So, all right. We solve for. I mean, we find this W, and once we substitute this W in the original problem, like this problem, the dual problem, then our problem that we have to solve now is, after substituting the value of W, is max of alpha transpose 1 minus half alpha transpose Y transpose X transpose X Y alpha, where alpha is less than equal to 0, right? And this is my dual problem. So now I have to maximize this with respect to alpha, where my original problem was minimizing norm of W star by 2 with respect to the constraint W transpose Xi Ya greater than equal to 1. So few benefits of doing this is, now we have this X transpose X in this part.
And how we will get this one, ma'am? One is this
one is just here. I mean, okay. So instead of this, you can write this as sum over alpha I raised from 1 to n.
Okay.
Unit vector.
This is what you will get. Okay. So what is the benefit of going with the dual problem here? We can see that here we have an X transpose X term, which is a covariance matrix, right? This is the kernel. We have.
You will get N cross N.
So dual will be in N cross N type. Earlier it was D cross N.
Yeah.
That's advantage.
This is N cross N. So the constraints are easier here, and what we can also see is that it can be kernelized. So if we have if the data set is not linearly separable, we can use the kernel method and we can also get the answer. So, all right. So what is the optimal W star that we got? The optimal W star that we had was sum over alpha I star Xi yi, where I is varying from 1 to n. And this alpha star, maybe we obtain it from solving this dual problem. Okay, and this is my W alpha star. So we can see from here, and what was the condition on alpha I was that it should be equal to 0. Right. So we can see from here that only the data points for which alpha i's are greater than 0, those points are contributing towards my W star, the optimal W star. Right? So how much important a data point is determined by this alpha I star.
Pardon, once again, ma'am. What did you told?
What I told is, you can see from here that your W star alpha is some linear combination of data point.
Yeah.
So, like, which data point is more important, or which data point are contributing towards my W star, is determined by my alpha star.
Okay.
right? Because if alpha is a 0, then in that case, that is not contributing to what my W star, right?
Yeah, yeah.
Okay. So the important points for us are the points for which alpha i's are
There are
different
two cases of alpha. Alpha is equal to 0 and greater than 0.
greater
Alpha
than
is
0.
0 is
But
not contributing.
the
Alpha
important,
greater than 0 is contributing.
yes.
Correct.
Okay.
Then
Ma'am, can you show me what is this alpha geometrically? Like, is it the bride?
Oh, which one? Alpha geometry. It's a vector, right? So
Yeah.
it's an alpha belongs to your alpha belongs to parent.
alpha is just a number, a scalar number, which
This
is,
is an Rn.
yeah, this is in
These
Rn.
alpha i's, yes, they are scalar. But if we talk about this vector alpha, it's I mean this alpha,
Yeah. If it is
it's
a vector, then it is a Rn, and then if it is a number, then it will manipulate the data point whether it is lying on that line or not, right?
what did you say? It will manipulate the data point.
The value of the alpha or the vector alpha will decide whether the value of this alpha I, xi, yi is 0 or not, right?
No, no,
No, no,
uh,
no, no. Sorry,
no.
sorry. If it is alpha is 0, the vector is 0, all the values of all the dimensions are 0, then it will not contribute to for the value of w.
See,
If
all this thing says is that if my alpha I r is this is 0, then those data points are not contributing towards my W star.
yeah, correct.
So only the points which are for which alpha I star are positive, they are contributing towards my W star.
Yeah,
So, bro, this alpha is basically a component of your hyperparameter C. No, you split the hyperparameter into two parts, alpha and beta. So you split
Yeah,
into
yeah,
alpha.
I get this, but I still have doubt regarding the soft margin SVM that alpha, beta, C, then sigma. I am very much confused about
No,
this.
you cannot get that geometrically, bro. You
no,
cannot get it.
here, what I understand, all the value of alpha are not greater than 0. All the value of greater than 0 is not valid for this W star. Only some values of alpha I, which is greater than 0, will contribute, and that we will get by getting the soft margin, that is
Yes,
SPM.
that will
Am I
be
right? Am I right, Nalo?
that will be a part of SVM, na?
Yeah, that is the part of SVM to find actual alpha I. Am I right, ma'am?
No,
Yeah,
what Abro is asking is a very valid question. He is asking geometrically how do you interpret
No, it is
alpha?
not possible because
It's not possible.
it
That's what
is
I'm
not
saying.
possible to
It
understand
is
that.
basically a number. It's a component of C, which is a hyperparameter. So you put C inside. You adjust, C between alpha and beta. So that's what geometrically you cannot have an interpretation because you just
Geometry will apply only in the two dimension only to understand the situation. The mathematics we are applying to get the solution. Am I right, ma'am?
no. Also geometrically also you cannot understand alpha. There is
No,
nothing,
no,
no
here
way
no.
to.
The two dimension we will able to
No.
do.
You will not understand alpha. You can only calculate.
We
See,
can.
alpha plus beta is equal to C, but
Yeah, that is
geometrically,
not possible. Yeah, yeah,
no. What that is what Abra is asking. Na?
yeah, yeah,
Is
yeah.
it possible to understand geometrically? I
No, no,
don't think we can understand.
no. Alpha is not possible.
Not
Correct.
possible.
okay. All right. So we got W star, right? So now, like when we look at the primal solution and the dual solution, the primal solution was my W star, and my dual solution is my alpha star, right? So, like when we look at the solution W star and alpha star, what we get is my alpha star G of W star has to be equal to 0. Okay, this is what we have seen. So, if W star is the primal solution and if alpha star is my dual solution, then this holds. So if this holds in our context, my G of W star is what? So my G of W star was 1 minus W transpose Xi by A, right? 1 minus W transpose Xi by A, right? So this is equal to 0 is what we say. And
that should be W star transpose now, madam. That should be 1 minus W star transpose.
sorry, W
W
star.
star transpose.
Now this is my complementary slackness condition.
Correct. This, yes.
Right? This is my complementary slackness condition, and all it says is that if one is 0, other has to be if one is non-zero, other has to be 0.
Has to be 0.
Yeah.
There are 3 cases possible. Both can be 0, or one non-zero, other can be 0, or GW star 0, non-zero, and alpha star 0. So 3 possibilities are there. So what now? If we look at this condition and what we had seen from W star, which is W star is equal to sum over alpha star Xi by I, right? And we had seen that those alphas which are positive are the points which are contributing towards my W star, right? So basically, we want alpha star to be greater than 0, right? Because of this. So we want alpha star to be positive. So if alpha star is positive, the second term has to be equal to 0 for this complementary slackness condition to hold. So what we get here is that 1 minus W star transpose Xi by I has to be 0. So for this to be 0, what can we say from here? We can say from here that my W star transpose Xi by I is equal to
1.
So this is the hyperplane.
Yeah, so this is the hyperplane. So how will it look like now? So if this is my W, if this is my W star, this is my decision boundary. These are my supporting hyperplane. So only the data points which are on this line are important to us. So given that my alpha star is positive, the data points which are important to us has to lie on the supporting hyperplane. So this is all it says. All right. So like where and these points for which alpha star is positive, and the points which lie on the supporting hyperplane, these points are called the support vectors. All these points that you see on, they are support vectors.
Whether all these data points or only the points which alpha star is greater than 0?
For which alpha star is positive.
Yeah, only for that value of that, right?
That's what I said, right? So for alpha star positive, all the points which you see on the supporting hyperplane, they are called the support vectors. And that's why this algorithm has gotten the name as support vector machine. So this W star is nothing but some sparse linear combination data point, because most of the data point will not lie on the supporting hyperplane, right? Most of it will be outside the supporting hyperplane, and if they are not contributing towards my W star. So only the data points for which my alpha stars are positive and they are on the supporting hyperplane, they are contributing towards my W star, and they are called the support vector. That's how this algorithm got the name support vector.
Once again, ma'am, go above just 2 lines. Just go back. Just go back. Yeah, here. No, go back. Yeah. A complementary selective condition. How we reach this alpha star G of W star is equal to 0 and alpha star 1 minus this? How we derived here? Go back. Just complementary selectness. How we got reached to this? What analogy we used here? Here. 2 lines. Yeah. Just
the proof we have already done it earlier, right?
Yeah.
I've shown it, but you can always go back and see. This is the complementary slackness condition that we get.
Yeah,
I mean, W star is the primal solution,
yeah,
alpha star is the dual solution.
yeah.
And based on that, I mean, you will get something and you will get this complementary slackness condition. See, we have already proved this. So,
Yeah, yeah, yeah,
this is
yeah.
a
Okay,
session.
okay. Same thing. The same thing. Yeah, yeah,
Yeah.
yeah, yeah. Okay, okay.
If,
Got it, got it.
always go back
Complementary
and
student. Yeah,
see more
yeah,
details.
yeah. It is lecture also. Okay, fine.
Yeah.
Yeah.
So not important for you to understand the proof right now, considering the exam is on.
Yeah, we can directly remember it. Na, we can use it.
You can directly remember that this is your complementary slackness
Okay,
condition.
okay,
If you
fine.
know the proof, how it, if you know the derivation, much better because.
Okay.
Yeah. So.
Man, there are two conditions for this complementary slackness condition.
There are the two conditions. One condition only, right?
Oh, so in soft margin we have two conditions.
In soft margin, we have two conditions because we have, I mean, there is alpha and beta term also coming into the picture.
Oh, yeah, okay, ma'am. Okay.
Some relationship between alpha, beta, and C.
Yeah, this is hard margin.
We are not going to soft margin. That we'll do on Friday. So week 10 will finish it at hard margin. From next, because week 11 also has a majority of the portion as soft margin, and in this week only a small introduction is given. So we'll keep this whole soft margin for the next class.
Madam, just empirically, what is the difference between hard margin and soft margin? How do you empirically mention?
So in soft, like in hard margin, what we are saying is that we are assuming that the data set is linearly separable, right?
Okay.
But in case the data set is not linearly separable,
okay,
then soft margin can be used.
Okay.
Yeah. So like we have seen some amount we can pay and move to the right side, right? We have seen all these things. We can pay some bribe.
So if it is linearly separable, it is soft. It is hard margin. If it is not linearly separable, it is soft margin.
No. If the data set is linearly separable, we'll use
hard margin.
And in case it is not linearly separable, soft margin can be used there.
So this is called as NP hard and NP hard.
No.
Different. That is different.
I'm getting confused with NP hard.
No, NP hard is something for which like we say for classification problem.
Okay.
We have the loss function, right?
Loss
and the function is if we want to find we want to minimize the indicator of h of xi not equal to yi.
Okay.
And this function, finding the solution of this loss function. I mean, minimizing this loss function.
Okay. The loss function becomes
very tough. I mean, this cannot be done in some polynomial time. So such problems are called the NP hard problem. You don't have to know the NP hard. I mean, NP hard, like what exactly it is, you can think of it as something for which you cannot find the solution in polynomial.
Okay, that we cannot find a solution in a polynomial.
Polynomial time means the limited time, ma'am, which can converge. It is the meaning of convergence like that, no?
See, I also don't know
what is the actual meaning of polynomial time.
Computer science terms. So maybe you can see it. So, NP hard is not something as soft margin or hard margin because nowhere related. Okay.
Understood. Let's change the topic. Let's go.
Okay. So yeah. So what we got is we got this solution. Now, if we are given any test data point, which is if we are given any x test, right, and we have to predict for this point, then what we will do? We will do W star transpose x test, right?
Yeah.
So after this, what is W star? W star is nothing but alpha I star
xi
yi transpose
x test.
Take the transpose x test, and this turns out to be alpha I star yi xi transpose x test. So if you have to predict for if you are given an X-test and if you have to predict the difference for this X-test, you can do W star transpose X1, and then you find the look for the time. That is how we can do it. So this is very important. Like, what is W star, right? This is very important. You should remember this. Okay. So this concludes SVM topic also. As soon as add margin as well. So in the next class, we will start with the soft margin estimate and do 11 plus.
Okay, ma'am.
Okay, madam.
Okay. All right.
Good
Okay.
revision. Good
night.
revision. We did confusions were to some extent deleted.
Especially the perceptron.
Perceptron is always perceptron. It is no conception.
Thanks for your explanation, madam. Thanks.
Yeah, thank you. Thank you, ma'am.
Thank you. All the best for exams.
Yeah,
Thanks.
thanks, ma'am.
Thank you.
Good night. Good night, everybody.
Good night, everyone.